Okay, I don't think so. So we'll be starting. Everyone, please start up your R Studio. We'll be dealing with probabilities. Okay, so far we have been looking at data sets and trying to make sense of the data that has been given to us, trying to compare means between two different groups and figuring out if the data makes sense. But in this case, our approach is a statistics based approach. That is, we have a data set on our hands and we want to make sense of the data. Today we are going to go in a different direction. We are going to learn about probability. As you would know, probability is essentially the understanding if like in probability you know what will happen. Say you toss a fair coin and you know how the times it will be heads and how the times it will be tails. You throw a dice, you know that it is 1/6 the probability that you will be getting a 6 or a 1 or whatever number that you want to get. So in case of probability, you actually know the truth of the data set, and from that you try to figure out if your particular dataset follows the true values that the dataset should have. So the idea of statistics and probability are all the time just looking at it from different directions. So in statistics, you know the dataset and you try to figure the truth of the dataset out. In probabilities, you know what the probability should have been and try to match your dataset to that specific probability. So, probability theory is a field of mathematics where different events occur, and you want to figure out first the likelihood of a particular event occurring, and testing your particular data set to that likelihood. So, in this case, we already know all the underlying probabilities, so you know the truth of the data set, and then you try to figure things out. The first thing that in this case that I would like you to know is what is a model of a system. So we have been talking about samplings a bit, how exactly samplings work. So you have a large, huge data set, say the entire population of heritage, and you just want to figure out how much marks they are getting in mathematics. So instead of going around and asking everyone, you take a small sample out of it and try to figure things out for that small sample. What you get is known as the statistic or the estimate for the population. The population has a particular already has a particular mean, which is known as the parameter of the dataset. So how would you get along with it? So instead of looking at the entire population, you make a model of the population. So model is essentially a simplified version of a system. For example, say you are looking at a city, but you would never uh, completely simulate the complexity of a city for us to easily analyze. So instead what we do, we use something like Google Maps to find our way across a city. So we use a city map to dial it down, to simplify into a digestible data set that we can easily figure out. So modeling an entire city as a map is something similar to what we do in statistics. Instead of working with complicated scenarios, we actually make a simplified model out of it and then work with that simple model to figure things out. Actually, I'm not able to see you guys. I will just display my screen. Yeah, that helps. Okay. Okay. So, yeah, I think that makes it clear. So, models are essentially simplified version of real life or complicated scenarios that we use to explain stuff in statistics. And here also probability and statistics differ. In probability models, we can easily say that something has a probability of 50% or something does not have a probability of 50%. But in case of statistics, it goes the other way around. You have the data and you try to infer a model. in case of probabilities, most of the time you know what the original probability should be. For example, if someone flips a coin 10 times and it gets you get 10 heads, you want to figure out if the coin is fair or not. So that is a statistical approach to determine if the probability of getting a heads is actually 50% or not, which in our case we know that a fair coin should have a 50% probability. Or if a lottery official spouse, so a lottery official's son or a lottery official's wife wins a lottery, can you really say that the lottery was not fair, or was it fair? So all of this is what we deal with in case of probability. So this is the first part of this is obviously going to be a revision of probability. I think everyone knows a bit about it, but we'll still go through it to refresh ourselves. So there are two approaches to probability. The ones that we have been dealing with most of our time is known as the frequentist approach. So in the frequentist approach, we know that flipping a coin 10 times, flipping a coin should be a 50-50 probability, being a heads or it being a tail. So say we do something like this. So so flipping a coin would be a like a easiest representation of a binomial thing. So a binomial model should be able to easily we should be using a binomial model, we should be able to emulate or simulate coin flipping. So using a binomial model to flip a coin. So we can do this using the function dbinom. We have three parameters. First is n. So n is the probability of getting heads, is the number of times you get heads or tails. Say out of you get n 5 times out of a total number of 10 times you have flipped a coin, and the probability is obviously going to be 0.5. So you guys can go ahead and try this out, see what you get. What is the probability that you are getting?
Sir, here it is saying that error in debinom unused argument n equals to 5.
Ah, it should be x. Try it with x.
0.246.
Okay, what does that mean, 0.246? How will you interpret that? Excuse me. Like, how will you interpret a 0.246 in it?
Like the probability of getting 5 heads over 10 chances is 24.6%.
Exactly. So it is like vaguely 25% chance that you will get 5 heads when you toss the coin 10 times. So it is obviously not 50%, right? We get it that wow, it is not 50%. So what went wrong? Like you flip the coin 10 times, even getting heads 5 times is around a 25%. So any idea, anyone?
So there is 50-50 chance, right? So it's not mandatory that there will be exact 5 heads and exact 5 tails. There can be anything, right?
Exactly. So doing it for a smaller population actually does not give you the exact answer that you need. So if I increase this to say 10, not, say to 1,000, and I try to get 500 heads, it goes even lower. Uh, hmm, Maybe it is. Let us try something else. If I do it for 20 times, and then we have 5 heads. Hmm. Ah, I get what the situation here is. It is just calculating for us to get just 5 heads or just 10 heads. Hmm, if I do it the other way. Okay, so essentially what I wanted to tell you is that if we have a smaller number of times we are doing the entire coin flipping, we will not get a 50% probability. The reason being that we are at a smaller scale. It is absolutely, as someone pointed out, that getting 5 heads is not mandatory. So even though the probability is 50%, you might not always get 5 heads and 5 tails. It might be some number in between the two of them. But as you increase the number of times you are flipping a coin, so you are flipping the coin 100 times, you are flipping the coin 1000 times, and we have done something like this in previous classes also, we see that the probability will tend towards 50%. It will never approach, like, till we flip the coin of infinite number of times, then is the only time when the probability will approach a 50%, which means that in the frequentist approach, if we flip a fair coin an infinite number of times, then the proportion of heads will converge towards a 50% probability, even though we know that the coin is fair and it should originally be a 50% probability. So, but the advantage of the frequentist approach is probability is based on actual real world observations, and it could be unambiguous. We know it is 50%, it should always be 50%, but it also depends that once you do an infinite number of trials or a very large number of trials, does the probability tend towards the value that you know. So it is very difficult in most real life world scenarios to figure out the probability of something occurring or not occurring using a frequentist approach. The other way around is called the Bayesian approach. The Bayesian approach is a bit different, and it depends on what you see by yourself. It defines a probability as a degree of belief an intelligent agent assigns to an event. So, say you are throwing the dice 10 times. How many times do you think the dice will throw up a 6? It would obviously not be 10 sixes. Even it will probably not even be like 1 by 6 times of 10, like 2 sixes all the time. It would be some value in between 2 and whatever. So even if you throw a dice 10 times, it could be magically that you get 10 sixes in a row. But does that say that the dice is unfair? It does not. We have, all of us have played, I think, Ludo once in a while, and you know there are multiple chances where you get 3 sixes in 3 turns. But with a 1 by 6 probability, it should not be possible, or the probability should be very low. In that case, you realize that maybe the frequentist approach is not the one you should go with. In that case, you go with something known as the Bayesian approach. In the Bayesian approach, there is the probability is determined by what you see. It is subjective to each one of the cases. So one way of thinking it is through rational betting probability. So probability changes each time that you actually do it. So the advantage it works for non-repeatable events. So say you were thinking, what is the probability of it raining tomorrow? That event will occur only once ever. Tomorrow will only come once. So say Monday. The probability of it raining on Monday 31st, it will only come around once forever. So you can't do a frequentist approach there because there are no infinite trials you can go through to figure out the probability. But you have to essentially believe subjectively what the probability should be and what is the probability of it raining the previous day, the day previous, or what is the probability of it raining the next day, and figure it out from there. So it is a subjective view of figuring out probabilities, and that allows it to be flexible. But in real life scenarios it is useful, but in statistics it is very difficult to actually simulate. Like, how will you simulate a particular subjective belief in a particular system where there are just numbers? So we are not going to be bothered with Bayesian view in this particular part. We are mostly going to deal with frequentist view, that we know what the probability should be and we increase the number of trials and figure it out from there. But in summary, the frequentist view can be too restrictive, because you have, even if the probability of tossing a coin and getting a heads is 50-50, we might, even after three coin tosses, get three heads. Absolutely possible. But on the other hand, the Bayesian approach can be too flexible and allow for you to figure it out for one-time events, for events at a very small scale, but different observers might have different probabilities. So I toss a coin three times, I get three heads. You toss a coin three times, you get three tails. So what will be the next result can be figured out both with frequentist and Bayesian approaches. So you would probably say the fourth will also be a tail because the last three were tails. So you have different probabilities depending on different observers. But frequentist view is what most of statistics depends on, so that is what we are going to deal with. So we are going to define a couple of things for it to be easy for us later on. This is basic probability, I know everyone knows this. So there is called something called an elementary event. So there is 10 different things that can occur. Say for our dice throwing experiment, elementary event will be the event in which a 6 comes up on the dice. So a single possible outcome of the experiment. Sample space is all the things that could happen. So 1 to 6, any one of them could come up, and those are the sample space. So 1, 2, 3, 4, 5, 6, all of the sample space, and 6 is our elementary event. Probability is the likelihood of the elementary event occurring. So a 6 coming up on the die, and that is represented, as we all know, by P of x. And P of x equal to 0 means something is impossible. P of x equal to 1 means it is always that thing that is true. We will take a very interesting example in which a person goes ahead, a statistician goes ahead and figures out the probability of him wearing a particular pair of pants. So him choosing a particular pair of pants, say a black, white, blue jeans, out of all the ones that he has, individually him choosing the blue jeans is a elementary event, and all the pants present in the wardrobe are the sample space that he can choose from. And a probability of 0 means he will never choose that particular pant, and probability x of it being 1 means that he always chooses to wear those pants. And the law of total probability suggests that the probability of all events, when you add it up, it will come to 1. That just makes sense. I hope everyone is with me so far. I think everyone is. This is just basic mathematics. So next we are going to talk about distributions. So a probability distribution just tells you how probable a particular thing is. So we are going to deal with this particular data frame in which we have made a data frame called pants. The different types of pants are blue jeans, gray jeans, black suit, and blue tracksuit. I am labeling them at x1, x2, x3, x4, and x5, and the probability is 0.5, 0.5, 0.3, 0.1, 0, and zero point 0.1. The probability of choosing any of them. And if I just display it, it will look something like this. Can you guys? So I will just, you know, copy and paste this into the. Something happened which I didn't want. Yeah, I will copy and paste this into the chat box. You guys can just copy and paste it onto your R studio inside a R code chunk and see that it works or not. Tell me when you have done it so that we can go forward.
That's it.
Okay, so you should see a data frame which looks like this. So blue jeans, gray jeans, black suit, blue tracksuit, and the probability of choosing all of them are 0.5, 0.3, 0.1, 0, and zero point 0.1. You have to make sure that probability of all of them adds to 1 because that is what the law of total probability tells you. So if we then plot a bar plot with pants and probability, if I choose a particular column, as we have done very many times already, a dollar sign helps me choose the particular column, and then the name argument is pants dollar type, which just gives us the name argument which can go in the x-axis. Please do this. And you should see something like this. So this is a bar plot in which blue jeans has a 50% probability, gray has around 0.3, black and blue are 0.1, and black jeans and blue tracksuit are at zero point 0.1, and black suit is at 0 probability.
So could you show the code again?
Yeah.
So the dollar sign here is
Dollar sign helps us
kind of
choose. Uh-huh.
like a subfolder type key, I guess.
Dollar sign helps us choose the column. So if I just do pants dollar sign type, it will give me the columns of the type column. So the variables under the type column it will show me. So this we have done also previously. We have used iris, sepal dot length. All of these we have used via dollar
Yeah.
sign. You just pick up the columns.
So here there's another column label. So what if we wanted to label the bar plot?
We have labeled the bar plot, right? We have put in the names argument and labeled the bar plot in the x-axis.
No, I meant that in the table, in the original table pants, in the
Yeah,
second column,
yeah, yeah.
it says x1, x2, x3, x4, x5. What if we wanted to label, uh, I mean, in addition to the x-axis saying blue jeans and gray jeans and black jeans, what if we wanted to label the columns with these x1 to x5 names?
Yeah, so that you can do, I guess. You can just make another label which would be, so this is just basic R, I guess. not types. What we want is label plus let's see what that gives us. There was a function for this, it was called C. Hmm. Should I do this? Aha, something like this. Oh, but it omitted. It is just not showing up in the bar graph, but this is something like similar to what you want, right? Hello.
Sir, can you show us the code once again? Yes, sir. Thank you. It's not. It's not showing, sir.
It is not showing what?
Like the thing is same as you. If
Yeah,
no other
what is
things will
happening
come.
is that bar plot is not showing because there is not enough space. If there was enough space, it would have showed. But essentially, this is what we
Oh,
want.
okay.
Okay.
So sorry, can you show it again? I'm getting an error.
Okay.
It says error incomplete expression.
In which line?
Oh wait, I think I didn't close the bracket. No, it's still showing. Oh, it happened. Okay, I was missing a bracket.
Okay. So essentially, this is what we wanted to see: blue jeans, black jeans, blue tracksuit. These are all the probabilities. And for non-elementary events, the probability. So say you wanted to find the probability of you wearing either a blue jeans or a black jeans or a black tracksuit. Not all of them will add up to 1. Independent events all add up to give you the event of a non-elementary event. So you want the probability of either blue jeans, black jeans, or blue tracksuit with the probability of you wearing either of the three. So these will be just a simple addition as long as all of these events are independent to each other. So this is just basic probability. Now we'll be trying to figure out probability for our particular questions. So to figure out different probabilities, we will be looking towards different types of distributions. So distributions we have figured out from previous classes are just the frequency of a particular event occurring versus the probability of the event occurring. So essentially, marks you are getting in a particular exam, so which how much marks you are getting and what is the scale of marks you are getting on the y-axis. So essentially, say how much marks you are getting in the x and how much marks are there in the y-axis. That will give you a distribution. Essentially, this is the idea is you can make various events actually, or various things in statistics follow particular distributions. They are bound by these rules, and we can use these distributions to plot different points and figure out the probabilities. So it is a mathematical function that gives you the probability of something occurring or something not occurring. So these are known as distributions. So binomial distribution is essentially the simplest that is there. It assumes that there is either a pass or a fail, or a true or a positive, a true or a negative to each of the events that you are considering, and you plot a distribution depending on that. Very easy to understand. Binomial distribution in case of a coin toss: if your coin flipping up or heads is a success, then you can plot it as a binomial distribution. And this is something that we have learned in class 12, how exactly a binomial distribution looks like. So I will just briefly show it to you. Yeah, Wikipedia. So this is what a binomial distribution looks like. We have seen this previously in, I think, class 12 or something, in which probability of success is P, the number of times success occurs is called K, and probability function would be the combination of n times K times P to the power K 1 minus P, which is the probability of failure, times n minus K. So we have looked at this previously, but we are not going to look at it mathematically. This is just what the figure looks like. We'll be using R functions to figure things out. So there are multiple things in case of binomial distributions. The first is called n. This you have to keep in mind is a big N, which is the total number of trials you are going through. So if we are taking the example of rolling a dice, the number of times you are rolling the dice is capital N. the probability here is given by theta, so number of times you can get individual successes is called theta, and that is in our case 1 by 6. If we figure out that, if my success depends on getting a 6, so that probability is only going to be 1 by 6 in a fair dice. And x is the variable representing the number of successes. So say you have been rolling the dice 20 times, and you figure out how many times you want to get 5 6s in a row, or 5 6s anywhere in the entire 20 rolls. So you using the dbinom function, you can figure it out. So x is the number of times you are rolling the dice, you want success, so x is the number of times you get a 6, size is the total number of times you have rolled the dice, and probability of getting probability of getting a 6 is 1 by 6. So if you just push it in, so you should get a probability looking like this. Everyone with me so far?
Yes, sir.
Okay, so if I want to find the probability of getting a 4 on the dice 4 times out of 20, what would be the probability, or how will you write the code? Anyone? So if you want to find a probability of getting a 4 times out of 20, how will you at least write the code? Anyone has any idea?
So the same as the previous, right? D binom x equals to 4, size equals to 20, and probability equals to 1 by 6.
Yeah, exactly. The code remains the same, because your now just your criteria of success has changed. The criteria of success has gone from getting a 6 to getting a 4, but all of the other things remain the same. You want 4 successes, the total size is 20, and probability of getting a success is 1 by 6. So it remains the same. Exactly correct. So what about a coin flip instead of a dice? If I wanted to get compute, I shouldn't have shown you the code. Okay, I will hide it and assume that you have not seen it. So if you want to compute 20 times getting heads out of 100 coin flips, what would the code look like?
So sorry, will you repeat?
If you try to, I will write it down so it's a bit easier. Find the probability of getting 20 heads out of 100 flips of a fair coin. How will you do that?
Sir, x equals to 20, size equals to 100, probability equals to half.
Exactly. And that comes around to 4.22 into 10 to the minus 10, which is incredibly low. Can anyone tell me why it's so low?
Because it's a very specific criteria. It has to come exactly 20 times, not more, not less.
Plus, if you look at the opposite end, you remember that we have been talking about the law of total probabilities. So, if you say it is coming 20 heads, then you have to say that there are 80 tails coming also. So, probably it essentially means that you are flipping a tail 80 out of 100 times, which is obviously very, very low. So, yes, it is very specific, and you have to always be looking out for the other end of it. So, because 80 tails coming out of 100 times, you realize how low that probability will be. So that is why it is so less. So if I do it as large as 50 times, then also the probability is pretty low, because getting 50 heads out of 100 is also a low. So this again comes up to our idea that frequent is like, we know that it should be a 50-50 probability, but getting 50 heads is pretty difficult out of only 100 throws. So this, using the function d binom, which actually works, so d essentially gives you the exact probability of something happening or not, is available for different distributions as well, which we will see a bit later on. But there are a number of other functions that are also provided. So d binom is for finding the probability mass function, essentially the probability of something happening or not. P binom is the cumulative probability function. So I think we have done something similar during mathematics in class 11 and 12, when we want to figure out what is the probability of getting 4 or less on a dice throw. When you have number of different, like you can either have a 1 or a 2 or a 3 or a 4. In that kind of cases, you use P binom, the cumulative mass function, a probability function. Then there is Q binom. Q binom gives you the opposite of P binom. We look at that. And R binom just generates these dice throws, so the number of successes. So for example, the probability of getting 0 to 6, 0 to 4, 0 to 4 sixes in 20 trials is given by P binom Q equal to 4, the fourth quantile, size is 20, and probability is 1 by 6. And you can do that and figure out the probability is pretty high. Like you get a 77% probability that you will either have a 0 or a 1 or a 2 or a 3 or a 4 sixes each time in the 20 throws. Is everyone with me so far? So out of the 20,
Sir,
yeah.
just one question.
Hmm.
So the p-binom function by default uh, assumes that the range is q for q, or the whatever variable we define first, is 0 to what we define.
Yes, so the number of success is 4 times or less. So it is a quantile function. So quantiles we have dealt with. 25th quantile means 25% of the entire thing or less. 75th quantile means 75% or less. Here fourth will mean
So
4.
what if
Yeah.
we wanted to find the probability of rolling 2 to 4 sixes? We wanted q to be less than greater than equals to 2 and less than equals to 4. Then would it work
Yeah,
with
so
p-binom?
even mathematically doing that, so if you remember us doing it mathematically, then also we will do something like this. So this is the probability of getting 2 or less. This is the probability getting 4 or less. So probability of getting just 3 and 4 will be the subtraction between the two. Make sense?
Got it. Thank you.
Yeah. Let's put a hashtag so that now no one gets confused. Everyone with me so far? Anyone has any questions?
So P binomial function is only for finding the probability in case of quantiles.
Yes, for P binomial is only for finding probability in case of quantiles. It is known as a cumulative mass function, probability function, in which you figure out whatever value you're putting in. This is the minimum number of successes, maximum number of successes. Even less than that many successes, what is the total probability?
Okay, sir. Thank you.
Yeah. So for example, if I put it as 10, so 10 or less number of times I'm getting a 6, probability is pretty high. And if I put it at 20, can anyone guess what would be the answer I get here? So my probability of getting 20 or less number of sixes if I roll 20 times. Any guesses? Anyone wants to guess? If you roll a dice 20 times, what is
Sir,
the
one.
yeah, one means
মানে surely আসবে.
sure, because obviously হবে না, because if I roll a dice 20 times, what is my probability of getting at least at most 26s? Think of it that way. Like, what is the probability of getting either 0, 1, 2, 3, 4 all the way to 26s out of a 20?
ও,
You will
স্যার
get
মানে সবকটা পসিবিলিটি কনসিডার হচ্ছে.
essentially সবকটাই probability আমরা কনসিডার করছি, তো obviously 1ই হবে. Did everyone else also follow this?
Yes, sir, done.
Okay. Okay. So P binomial gives us a cumulative frequency for whatever quantile we are considering and less than that. The opposite function is called Q binomial. So since so here the idea is that how, so what is the probability, if my probability is 0.75, then how many times will I get a 6 or not? So the here I will figure out the percentile, so the opposite to this. So here if I was putting in 4, so getting 4 or less successes is 76% probable. So if I ask the opposite question, what is 76% probable, or what is 75% probable if I throw the dice 20 times? So the answer is 4. So you get 4 or less say times you get success. So if I reduce this to 50, my number of successes drop to 3 or less. So this gives you the quantile or the cumulative probability, the cumulative number of successes that can occur. So you can either have 0 successes, 1, 2, or 3 successes if your probability is 50%. So just the opposite function to p binomial. Okay, moving on. Finally, we have been talking about number of successes using the p, q, and d binomial functions to figure out the probability. But what if you actually want to see that in your see that actually? So you want to make a distribution, actually make a distribution. So if I roll, so I will show it to you in a bit different way. So how R binomial works is that R binomial randomly generates a particular value, or depending on the probability that you have been giving it. So essentially this says that I want to roll my dice 20 times. The probability of success is 1 by 6, and I am only rolling it once. So what will I see on my dice? You will see 6 times you get a 6. So again, telling you this again, our binomial functions via these two parameters are fixed. So the size is the number of times you are repeating the dice throw. Probability is 1 by 6 of getting a 6, and you just roll it once. When you just do 20 throws of the dice, then there are 6 times that you are getting a success. This is what the R binomial function tells you. It randomly generates the number of successes that you will get depending on the total number of size of your dice throws and the total probability. And essentially this is not just used for this. Oh, okay, we got disconnected. Very nice, very nice. Yeah, thank you. New meeting, start instant meeting, do that. Okay, I think everyone has rejoined. This time we didn't even get a message from Google that the meeting was going to end. It just ended. Okay, coming back to where we were. R binom. R binom randomly generates the number of time you will get a success in a particular trial if you put in n equal to 1. So number of times I'm getting a 6 if I throw the dice 20 times, and the total probability is 1 by 6. So if every time this will be random. So previously we got a 2, next time we got a 6, and essentially R binom is used to simulate multiple rounds of a particular experiment. So say a particular my experiment was throwing the dice 20 times and getting a 6. So it can either be all the way from 0 number of sixes to 20 number of sixes. What if I want to do it 100 times at once? So you just put in 100 here, and you will get a randomly generated number of successes. So out of all of these, essentially R, what it has done, has thrown the dice 20 times and just written down number of times it has gotten a success. So it can go from all the way from anywhere from 0 to 20. And if I draw a histogram for this, you will see that the histogram has a particular peak, and it follows a particular curve. Most of the times you will get a 6 falls around 2.
Sir, can you repeat? Your voice was
Breaking up. Okay.
on.
Yeah, so what I want to say is that R binom generates. So if you put it at n equal to 1, R binom essentially generates that if you throw the dice 20 times and the probability of getting a success is 1 by 6, then what is the number of successes that you will get? So the number of successes I will get is 3. So 3 times out of 20 I will be able to throw a 6. Essentially R binom is used to repeat the entire binomial experiment any times you want. So my experiment is throwing the dice 20 times and looking at the number of times I get a 6, which is success for me. So essentially I can repeat it any number of times I want. So if I put n equal to 100, what R binom is doing is that it is throwing the dice 20 times and counting the number of times it is getting a success, and that it is doing 100 times. So each one of these values essentially says that yes, I have thrown the dice 20 times and I have counted number of times I am getting a 6, and I am repeating the entire thing 100 times. So these are all the values I am getting, and I can even plot them, and you get a interesting looking curve where you have one peak and two tails on both ends. So these are the types of distributions that we have been looking at for a long time, and this is what you know call a binomial distribution, in which you are essentially doing a binomial experiment and plotting the frequency of success, and on the x-axis, essentially on the left hand side, you are plotting the frequency of successes, and you on the right hand side x-axis you are plotting the number of successes in each of the trials. So this is essentially the binomial distribution. So to better understand it, let us try doing it for coins. So say I had my binomial distribution was this time around, I am tossing a coin 100 times, and heads is my like success criteria. So how many times out of 100 will I get a head? So randomly generated, it is saying that you will get 55 heads out of 100 if you do it 100 tosses. If I repeat the experiment 100 times, then you see most of it, my number of heads like very close to 50. So it looks something like this. If I continue increasing it, You see it is taking the shape of a, what is this distribution called, guys? We have looked at this distribution before.
So normal distribution.
Yeah, exactly. It looks like a normal distribution. So this always happens that many distributions tend towards normal distributions when we look at it for a large number of observations. And to test if it is a normal distribution, we use the Shapiro test. That is also something we have done. And the Shapiro test, what is this? The sample size must be between 3 and 5. That is unfortunate.
So what is Shapiro test?
Shapiro test we have looked at before. So it tests the normality of a particular data set. So it checks if your data set is actually normal or not.
Okay, sir.
Uh, so why do we care about normalcy? Because most of our data that we look at, most of the tests that we run, t-test, ANOVA, this, that, everything, all of them actually follow normality. So they assume that the data set is normal. So this is something that we were discussing last class also, that before running an ANOVA you should check if your data set follows a normalcy or not. So here we see that the p-value is 0 less than 0.05, so it is not normal per se, but it is close. But essentially here what I want to tell you is that using R binomial you can generate different values of all the successes, essentially repeat your particular binomial experiment. Okay, so everyone okay with this? Anyone has any questions with the binomial distribution functions? Okay, so we go to the next part, which is so we have looked at the binomial distribution and how it works. Next we will be looking at the normal distribution, the most well-known distribution, which is also known as the Gaussian distribution. So most of distributions in the nature actually end up following the normal distribution, as we just saw that when we did the binomial distribution for a very large number of values, it actually looked very similar to the normal distribution. Doing it again, you see it looks very similar to normal distribution. So normal distribution is very characterized and well known, and we'll be looking at that next. So the most well-known probability distribution is known as the normal distribution, as we just saw. It is so our binomial distribution was characterized by two variables. If you would remember, it was, yeah, binomial distribution is characterized by two variables: the probability of a success and the number of trials. Instead, our normal distribution also has two variables, but the variables are the mean of the particular distribution and the standard deviation of the particular distribution. So we have already dealt with mean and the standard deviation. Mean is just the central tendency of a particular distribution, and standard deviation is how far away the particular values lie from the mean. Now, interestingly, all the functions still look very same. D norm computes the probability density, P norm computes the cumulative probabilities, Q norm is just the opposite of P norm and gives you the quantiles, and R norm generates random numbers which follow normal distribution. So yeah, so we will try doing that. So first thing we can do is that generate 100 random points according to normal distribution, and when you do not, here are in R binomial you have to put in the number of uh, the number of times you're repeating or number of random number generations you want, and the size and the probability. Here you can actually put in just R norm without any of the other variables, because the normal default values for R norm are that the mean is equal to 0. So the mean equal to 0 and SD is equal to 1. For normal distribution, this is the default values. So if you don't put in anything, R will take just that, and you can draw it, and you see a normal looking distribution, but since the number of random variables is so small, you don't see the normal curve. But you increase it, you actually look and see that the curve is actually generating normal values. So this is just and this is the mean. You see that the mean is solidly at 0 and the SD is around 1. Everyone with me so far?
Sir, can you explain once more?
So we have looked at binomial distribution. Binomial distribution can be easily used to simulate success or failure, in which we know the probability very nicely. But next we are going to look at normal distribution. Normal distribution is the most well-known one out of all probability distributions, and most of our like whatever experiments we do, they always tend to end up as a normal distribution, so it is very nice to know it. So in case of normal distribution, there are two values that we have to put into the R norm or P norm or D norm, all these functions, which are the mean of the distribution and the standard deviation of the distribution. So in this case, we are generating 100,000 random normal variables, and here we are not putting in the mean or the SD, because by default R takes the mean and SD of normal distribution as 1 and 0 and 1 respectively. So if you want a distribution of that nature, then you don't need to put in any values. But if you want to put in values which are are different, say you wanted to put in values of IQ, where the mean of the entire population you're looking for is 100 and the SD is 10, then also it will generate a random distribution for you. So very less people are very smart, around a 130 140 IQ, and a lot of people are around the 100 IQ level, and a less amount of them are around 60 or 70. Make sense?
Yes, sir.
Okay. So next we will be looking at how exactly the shape of the normal distribution curve changes throughout. So this is a lot of lines. Essentially, I will just
Sir, can you explain the third line? Can you explain the third line there? That is after histogram.
ab line is just this dotted line that you see. It is just plotting the dotted line at the mean. It is doing nothing else,
Okay.
plotting a dotted line at the mean to show that yeah, mean lies here.
Okay.
Yeah. So next we will be looking at how mean and standard deviation changes the normal distribution. So I'm not asking you to write it down, just look at it. Okay. If you look at the left graph, you see that mean shifting the mean from 0 to 1, 0 to 3. So mu is the mean. In for the red distribution it is 0, for the blue distribution it is 3. You see that the peaks are actually different. So the peak is what the mean determines. It determines if the where the peak of the normal distribution will be, whereas sigma, which is the standard deviation, determines how narrow the distribution would be. So how thicker its tails would be and how taller its peak would be. So both of these distributions have a mean of 1. So both of them have a peak at 1. But for the red distribution, the standard deviation is 1. So we have a flatter curve with heavier tails, whereas if the standard deviation is 0.5, that is the values are much more closer to the mean of the entire distribution, we have a narrower curve. So it is, very tall and very short tails, very small tails. We don't have values that go around this area. We have very low values in this area and very high values up here, essentially here. So mean determines where the peak will lie. Standard deviation will determine how flat the curve is. Everyone with me?
Yes, sir.
Okay, so that was all about normal distribution. Like, designing experiments for normal distribution is not something that we all cover in this course. It becomes a bit difficult. I will just show you different distributions and how to plot them. you know Feel free to play around with them and learn more about them, but essentially just that. From normal distribution, I would just like you to know that the Shapiro test is used to test the normality. And yeah, if the Shapiro-Wilk test gives you a value, the p-value is not significant, that means that the particular distribution is normal. If the p-value is significant, that is less than 0.05, then the entire distribution is not normal. So significant Shapiro-Wilk test, not normal. Not significant Shapiro-Wilk test means normal. Okay, moving on, we have a different distribution called the Poisson distribution. Poisson distribution occurs when the number of events occur at a fixed interval with a constant lambda. So essentially, if there is something occurring every particular time point, say the classes change at, like, the classes you have at heritage, they are, if I remember correctly, those were 50 minutes long. So every 50 minutes the class changes. So in such a case, you use the Poisson distribution, and the function again remain the same. The R poise, D, P and Q Poisson. It is just the particular parameter that you are dealing with. Then there is something called the gamma distribution, which is very right skewed, which looks very much similar to an exponential curve, but actually it is not. It is just useful for modeling waiting times. So if you have been it looks very similar to doubling times, but it has a particular specific use. But again, a different, what do you call it, functions remain the same, so very easy to use. Finally, yeah, someone has a question? Okay, I don't think so. We can skip. Yeah, again, if someone tells you, so if, say, your friend was looking at a lot of probabilities, a lot of distributions, he came up with a very weird looking distribution. He made a normal distribution using these parameters and a Poisson distribution using these parameters, and then he out of nowhere asked you, tell me if this particular distribution is normal or not. So you don't have to be afraid. It doesn't matter what distribution he gives you. You just have to run a Shapiro-Wilk test, and then that gives you an idea if the particular, what why is it not running? Run, please. No. Is something else running? Yeah, this ran. What? Okay, that is strange. Uh, there. No, no, no. There. Now will it run? Yeah, it is run. So whatever. So this particular distribution, which is a random combination of normal and Poisson distribution, and then on top of that you do some mathematics, it is not normal. and that can be just be figured out using a Shapiro-Wilk test. And this is what the entire distribution looks like, which looks very difficult. This is a density plot, which obviously does not look anything like a normal distribution, and this is how you figure out the distribution is normal or not. Okay, so that is all I think we had to deal with regarding probability and distributions. That is all I have for today. Any questions anyone has?
স্যার
Yes.
স্যার এখানে ওই টাইপের কোশ্চেন করতে পারি, লাইক tossing two coins simultaneously, then
হ্যাঁ করা যেতে পারে, but you will have to ask the question very nicely. Let us see. Uh, yeah, বলো question বলো. So say so you will have to figure out how to pose the question and then write it down in code. Say find the probability of getting a 6 on a coin toss and a 6 on a coin toss অসাধারণ, head on a coin toss and a 6 on a fair dice. So if I wanted to do this, how will I do this? বলো কেউ একজন. Here just the idea, this is just a basic probability idea, but if you have p of a particular event and you want to figure p is essentially two different independent events pulled together, then it is just a multiplication of the probabilities, right? If you would remember from probability things, independent events both occurring at the same time, so you multiply them and you figure them out. It is very easy to deal with independent events. If they are not independent, then you have to use a Bayesian approach, which we don't want to do. So if I just write, if my x equal to is getting ahead and my size is also is 1, because I'm doing it once, probability is half and multiplied by d binom, again x equal to 1, size is again 1 because I'm just doing it once, probability is 1 by 6, and yeah, this is the probability of getting a head on a coin toss and a 6 on a dice at the same time. চলবে?
thank you, sir.
Okay, so brush upon basic probability because next assignment will have a lot of probability stuff in it. So yeah, I mean I have not gone through all the things about probability because I thought I believe that everyone knows probability, but yeah, just একবার revise, huh? ঠিক আছে, so this was all I had for today. I will just quickly take your attendance and I will send you guys the assignments by tonight. Can anyone tell me, there were just 12 groups, right? Can anyone confirm?
স্যার 13।
13 কখন হলো?
স্যার লাস্টে একটা গ্রুপ হয়েছিল, রাইট? যেটা আপনি ফর্ম করে দিয়েছিলেন।
হ্যাঁ আমি সেটা কাউন্ট করিনি, ঠিক আছে। 13 group will get a different assignment then. Let's see. ঠিক আছে, okay.
স্যার এগুলো কি আপনাকে লিখে দিতে হবে, লাইক মেলে পাঠাতে হবে, দিস গ্রুপ লিস্ট?
Group list, yes, that would be the best thing to do. The group list তোমরা একবার someone collate the number of groups, group 1 to 13, তার নামগুলো লিখে just send me one mail, ঠিক আছে? Someone take responsibility for it and send me one mail.
ওকে, আমি পাঠিয়ে দেবো।
হ্যাঁ, ঠিক আছে, প্লিজ
আমি
ডু দ্যাট।
পাঠিয়ে দেবো।
অ্যান্ড আমি অ্যাসাইনমেন্ট গুলো লিখে পাঠিয়ে দেবো। দ্য অ্যাসাইনমেন্ট উইল বি based on our notebooks, so you will have to put the entire assignment in there. So there will be like multiple questions, কতগুলো will be about coding, কতগুলো will be about analytical understanding of what you are coding, and everything should be on our notebook, and our notebook you will send me back. Okay,
Okay, sir.
ঠিক আছে। Thank you everyone for joining today. See you next week. Thank you.
Thank you, sir.